All right. So for number 8, if W and Z are independent, that doesn't mean that the means are equal to each other. It doesn't mean the variances are equal. It also doesn't mean that the probabilities are equal at all. It means that they're uncorrelated from each other. And the definition of independence here is that the probability of W equals lowercase w, Z equals lowercase z. So the whole point of independence is that the and here becomes multiplication. So we can say the z equals z times probability W equals W. Right. So this problem is really about this distribution for y. And in this particular case, she has 10 questions, so 10 trials. And on each question, she has an 80% chance of getting correct, 20% chance of not getting correct, right? So each trial is a Bernoulli. There's 10 of them. So this is a binomial distribution. It's binomial with 10 trials and probability of success 0.8. Okay. And so when we say probability y is greater than or equal to 0.9, it's a binomial variable. So we use the binomial formula. And when since it's discrete, we can separate this out into y equals 9 plus y equals 10. And this first one is 10 choose 9, meaning out of the 10 total questions, you choose 9 of them to be correct. 0.8 to the 9 because 9 of them are correct. So you do the correct probability, 0.8 to the 9th power, and then the incorrect probability, 0.2 to the first power. Okay. And then similarly for 10 choose 10, we're going to do it for probability y equals 10. It's going to be 0.8 to the 10th times 0.2. And since here you get all of them correct, none of them incorrect, so this is going to be to the 0. All right. For expected value of y, again, you just use the formula sheet. So once you recognize this binomial, the formula says n times p, in this case 10 times 0.8, which is just 8. So on average, she's going to get 8 questions correct. Okay. Let x be the outcome on the first question. So not 10 questions anymore, but just the first question. So this distribution is now a Bernoulli because it's the same as before, right? Each of them has a yes or no, but now there's only one trial. There's not 10 trials. So that's why that's the definition of Bernoulli, right? And so we would say it's a Bernoulli with probability 0.8. Okay. And consider the number of questions out of 10 that Kirti will get correct, conditional on the first answer being correct, right? So if you already know that the first one is correct, that's not going to affect your performance on the other 9, right? So it's still going to be binomial. But now you already know one of them is correct, so it's only 9 trials left, and then with probability of 0.8 on each question. Okay, and so it says what is the probability y is greater than or equal to 9 given x equals 1, right? So I already know that I got the first question correct. Okay, and I am trying to figure out what's the probability that I get at least 8 more correct, right? So this is actually the same as just probability that y is either 8 or 9, right? Because I already know that I got one of them correct. I already got the first one correct. So I'm really just checking the other 9 questions, right? So I can either get 8 of them correct or I can get 9 of them correct. Okay. And so again, like before, this is binomial. So it's 10 choose 8. 0.8, or sorry, not 10 choose 8. It's 9 choose 8, right? Because you already got the first one correct, is 9 choose 8. 0.8 to the 8, 0.2 to the 1. And then for the second one, for the y equals 9 is 9 choose 9. 0.8 to the 9. 0.2 to the 0. Okay. And what is the expected value of y given that x equals 1? Expected value of y given x equals 1 is n times p, right? So there's 9 questions, and each of them you have a 0.8 chance. And then you also are getting 1 for free because you always get the first one correct, right? So you're getting 1 plus 9 times 0.8, which is 8.2. So it's a little bit higher, right? As you can see, like this one, we got 8. And then now that I know for sure I got the first one correct, it increases expected value a little bit because one of them is guaranteed now. Okay, so for problem number 12, we're talking about labor underutilization. Yeah. So we're trying to figure out how many people would like to work more hours, right? So XI is either underemployed or employed how you like, right? So what is the probability XI equals 0, right? So this is the probability that this person is employed like how they want to be employed, right? This is 80%. Probability XI equals 1 is 20%. That's just given in the problem. What is the probability that P hat is equal to 0, right? So P hat is the values of the first four members, X1, X2, X3, X4 over 4. It's the simple average of the first four members, right? That you survey. So what are the possible values this could take, right? So P hat could be, well, if all the X's are zeros, then it could be 0. If this X is 1 and then the rest of them are zeros, then it could be 1/4, right? If these two are 1 and the rest of them are zeros, then it could be 2/4 or 1/2, and then it could be 3/4, and then it could be all of them are 1s, which would cause it to just become 1. Okay. Okay, and so we want to find these are the possible values P hat could take, so we want to find the probability of each of these, right? So in the case of probability P hat equals 0, right? The only way for P hat to be 0 is if all of these people are 0, right? That's what we just found. So that means out of the 4 people, none of them are underemployed, right? All of them have the employment they like. And the probability of that happening is 0.2 to the 0 power, 0.8 to the 4 power. For probability P hat equals 1/4, that means out of these 4 people, one of them is underemployed and the remaining of them are doing what they want, right? So out of the 4, we choose one of them to be underemployed. Okay, and then same thing like 2/4, right? So that means 2 of these out of all 4 of them is going to be underemployed. The other 2 are going to be not underemployed. So it's going to be 4 choose 2, 0.2 to the 2, 0.8 to the 2. And then for 12.6, right? So we have probability P hat is 3/4. I think you're seeing the pattern, right? It's going to be 4 choose 3. 0.2 to the 3, 0.8 to the 1. And then lastly, probability P hat equals 1 equals 4 choose 4, 0.2 to the 4, 0.8 to the 0. Okay. So it's actually a binomial problem in that sense, right? Because the P hat is based on what the Xi's will do, right? So it's similar to a binomial in that sense. Okay, what is the expected value of Xi? Well, for Bernoulli variables, that's just going to be just P, and the P here is 0.2, right? That's what we got in 12.2. What is the expected value of P hat? Well, expected value of P hat, you could either calculate it out by doing, each of those values times each of the probabilities. That's fine too. But this is something we talked about in one of the homeworks. If we just write in the formula for P hat, X1 plus X2 plus X4, 4. We use our expected value rule, so we can pull out the 1/4 and then separate over the addition. So it becomes like a bunch of expected values that you can add up, right? And each of these is what we already got in problem 12.8, right? We just got this as 0.2. So it's going to, and they're all the same, right? Because they're all from the same distribution. So it's 0.2, 2 plus 0.2, 0.2. So there's 4 of them. So it's 4 times 0.2 times a 4th. So it's just going to end up being 0.2 as well, right? So in general, anytime you have the sample mean, that's going to have the same expected value as each of the individual observations. Okay, and the standard deviation here, you can calculate that using the standard deviation formula, and similarly for the standard deviation of P hat, right? So you can use the method that I just showed here using the equation and plugging it in and using the properties, or you can use the other method where you like literally just use the formula, expected value of X squared, or expected value of P hat squared minus expected value of P hat whole thing squared. So the expected value of xi is the unemployment rate, which is 5%. And this, as we talked about before, right, the mean of the sampling distribution, p hat, because it's like the sample mean, is going to be the same as, it's going to have the same expected value. It's going to have the same mean as the original variables, right? The standard deviation of xi, well, for Bernoulli, that's going to be p times 1 minus p, which is, 0.05 times 0.95. And for p hat, and we talked about this before too, right? That the it's going to be the same as the standard deviation of xi, but divided by square root of the number of observations. So in this case, it's like 0.05 times 0.95. So that's just from 14.3. But then you divide by square root of 500 because that's how many people you have. Okay. What is the probability that more than 6% of the labor force members in your sample will be unemployed, right? So that what it's asking, what is the probability that p hat is greater than greater than or equal to whatever 6%, right? So we can convert this to a normal distribution by subtracting the mean divided by the standard deviation. So we get p hat minus what we got in 14.2, right, which was 0.05, divided by what we got in 14.4, which was 0.05 times 0.95, divided by square root of 500. And we're trying to find when is this greater than 0.06, and the same things, 0.05 minus 0.05 divided by 0.05 minus 0.95. So we're converting this to a z-score, right? Over square root of 500. Okay. And then then it's just a standard normal problem, and you look this up in the z table. Okay. And this 14.6 is the same, except instead of 6%, it has between 4.5% and 5.5%. But it's the same thing. You just convert these to z-scores by subtracting the mean from 14.2, divide by the standard deviation from 14.4. Okay, so after you do that, then you just look up those z values in the z table and then subtract for these. Right? P hat is equal to x1 plus x2 plus x3, right? 3 students, and you're just taking the sample mean of them. Okay. What is the expected value? As we talked about before, the expected value is the same as each of the individual x's, and each of the individual x's could be will have a probability of 0.2, right? So it's going to be just 0.2. Standard deviation is going to be the same as the standard deviation for each of the individual x's, so it's going to be 0.2 times 1 minus 0.2, but you have to divide by the square root of the number of samples, so square root of 3 in this case. Okay. And then derive the PMF of P. So this is similar to the previous problem, right? It could be 0. This is if all of the students are not in a fraternity or sorority, right? So it could be 0. And this happens only if all of them are 0. So out of the 3 students, none of them are in a fraternity, right? Which is 0.2 to the 0, 0.8 to the 3. Similarly, probability p hat equals 1/3. 3 choose 1. 2 to the 1. 0.8 to the 2. Right, so out of the 3 students, one of them's in a fraternity, so it's 0.2 to the 1. 2 of them are not in a fraternity, so it's 0.8 to the 2. Right, and it's going to be similar for 2/3 and also for 1, right? So for probability p hat equals 2/3, it's the same thing. And for probability p hat equals 1, it's the same thing. Okay, so it's kind of this is the kind of problem that's kind of like binomial. Okay. Number 18 in the United States, 40% of people drop out. So if you conduct a random sample of 1,000 people, what is the probability that the estimated dropouts between 38 and 42, right? So this is again a z-score problem. So we're trying to find probability that 0.38 is less than p hat is less than 0.42. And so as before, we subtract the mean and divide by the standard deviation, right? So it's going to be the mean here is 0.4. So it's 0.38 minus 0.4. And then the standard deviation is 0.4 times 1 minus 0.4, so 0.6. I'm just gonna write it all the way out though. Divided by square root of the number of samples here, which is 1,000. Okay, and that's gonna be your lower z-score that you look up, and then your higher z-score that you look up is, it's pretty similar. It's 0.42 minus 0.4 over 0.4, 1 minus 0.4 over square root of 1,000. Okay, so a lot of these problems for confidence intervals and stuff have the same method, which is just that you have to convert the numbers here to z-scores, right? So you have to subtract the mean, divide by standard deviation. That's always what you do to standardize back to a z-score. Okay, good. So for problem number 20, describe the shape, mean, and standard deviation of the sample mean, right? So the shape is going to be, because there's 125 houses, there's quite a few houses. Because of the central limit theorem, we say this is a normal distribution. So it's like symmetric. Okay. The mean, we can say symmetric. The mean is going to be the same, 36,000. And the standard deviation is going to be the same as the standard deviation, but divided by square root of the number of houses. So it's 17,000 divided by square root of the number of houses, which is 125. So for this confidence interval, we do something similar. We have to, first of all, look up this value in the Z table. And in particular, we have to look up half of the missing percentage. So how much is missing? So it's 90% is covered. So there's 10% missing. Half of that is 5%. So we're going to go to our Z table and look up 5%. Okay. So we're looking for 5% in the middle of the table. Which is right. So this is 0.03, 0.04. 5% is like right here somewhere. Negative 1.64, negative 1.65. Okay, so that's the value we're going to use as our kind of important Z star. Okay, so we'll use Z star as, I'm just going to go 1.64, but you could go 1.65, it doesn't matter, right? Okay, and so the way you set up a confidence interval is you do the mean plus or minus the Z star we just got at times the standard deviation divided by square root of the number of samples, right? So in this case, we have 23.6. That's given to us in the problem, plus or minus the Z value that we have to look up because the 90% confidence interval is 1.64. Okay. And then times the standard deviation, which is 7, divided by the square root of the number of students, which is square root of 100. Okay, so the plus will give you your upper bound, the minus will give you your lower bound. So this is how you get a confidence interval. So in order to create the margin of error of this confidence interval is just $50. So margin of error is the part after the plus or minus. So that was the Z star times standard deviation over square root of n, right? So in this problem, it's giving you that you're looking at a 95% confidence interval, and we see it's like 1.96 right here. So Z star is 1.96. 96. The standard deviation is given to us is 1,500. Okay, and then so we want the margin of error to be $50. And again, this has the formula Z star times S over square root of n. And I know Z star and I know S, right? So it's 50 equals 1.96 times 1,500 over square root of n. And then you just solve for n. Whatever n you get, that's going to be the answer. Okay. And if you want to be really precise, you would say like n is greater than or equal to whatever you get. N is equal to is fine. It's technically going to be n is greater than or equal to.